Everything we rely on, our phones, our laptops, and especially electric cars, is hungry for better batteries. We need them to last longer, charge faster, and hold more power. Well, there's a global race happening right now to find the next big thing in battery tech, and one element is stealing the spotlight: silicon. So let's get into why scientists are so incredibly excited and, frankly, so frustrated by this one material. All right, so in any lithium-ion battery, you've got this crucial part called the anode. For decades, the undisputed champion of anodes has been graphite. It's stable, it's pretty cheap, and it's in almost every battery you own. But there's a new challenger on the scene, one that could totally change the game when it comes to energy density. And yep, that challenger is silicon. So let's talk numbers for a second. Graphite, our current champ, has a maximum theoretical capacity of 372 milliamp hours per gram. That's been the gold standard for years. But here's the thing. We've pretty much pushed it to its absolute limit. There's not much more performance we can squeeze out of it. Okay, now compare that to silicon. Its theoretical capacity, around 4,200 milliamp hours per gram. Whoa, that is not just a little better, that is a massive revolutionary leap forward. We are talking about more than 10 times the energy storage for the same amount of weight. This is the number that has the entire battery world buzzing. And really, this tenfold promise is what this is all about. Just think about it. An electric car that could go 2, maybe even 3 times farther on a single charge. A smartphone that lasts for days, not hours. That is the kind of potential we're talking about here. It's a true generational shift in technology, just waiting to be unlocked. Which, of course, leads to the big question. If silicone is this amazing 10 times better miracle material, what's the catch, right? Why isn't it already in every single battery we use? Well, it turns out this powerful titan has a seriously destructive, fatal flaw. Yup, all that incredible potential comes with a massive, massive challenge. It's a problem that has kept silicon out of mainstream batteries for years, and it all comes down to some simple physics that has some pretty catastrophic consequences. Okay, here it is, volume expansion. When you charge a silicon anode, it soaks up lithium ions like a sponge. But as it does that, it swells and swells up to 300% of its original size. Then, when the battery discharges, it shrinks all the way back down. Can you imagine something inside your phone inflating to 3 times its size and then deflating over and over again? It's not going to end well. And the results are, well, disastrous. This constant, huge expansion and contraction literally pulverizes the silicon. It turns the carefully engineered material into dust. This causes the whole anode to crack and just peel away, breaking all the electrical connections. And just like that, the battery dies. Fast. You don't have to take my word for it. This quote from the research sums it up perfectly. It's that huge interface stress from the volume change that's the real killer. This isn't just a minor issue, it's a fundamental hurdle we have to clear to get to all that power. But, and this is where the story gets really, really cool, instead of just giving up, scientists have completely reframed the problem. They thought, okay, if it breaks apart on a big scale, what if we engineer it on a super, super tiny scale? They've come up with some brilliant ways to tame this titan, 1 nanometer at a time. Right now, there are 3 main strategies that are leading the pack, and each one is a different, clever way to solve that expansion problem. We're going to look at the core shell structure, the porous and hollow design, and the nanowire approach. The first strategy is so elegant. It's called the core shell structure. Picture taking a teeny tiny particle of silicon, that's the core, and wrapping it in a tough but flexible outer layer, like a shell made of carbon. That shell acts like a suit of armor, physically containing the silicon as it swells and shrinks, stopping it from turning into dust. All right, the next approach is just as smart, but it tackles the problem from the inside out. Instead of wrapping the silicon, you create silicon structures that are already full of tiny holes, making them porous or even hollow. This way, you're giving the material built-in empty space to expand into, so when it swells, it just fills up those internal voids without stressing the whole structure. Genius! And finally, we have the nanowire approach. This one is all about changing the fundamental shape. Instead of little balls of silicon, scientists grow these tiny, flexible pillars. Think about it. A solid floor will crack under stress, but these little pillars can bend and swell and move around without breaking. Plus, they create a superhighway for electrons to travel. So here we are with three incredible, clever nanoscale solutions. In the lab, they all work amazingly well. They solve the expansion problem and create stable, super high-capacity batteries. But now comes the next big hurdle, going from a single successful experiment in a lab to a factory that can churn out millions of these things. Because here's the reality check. A breakthrough in the lab is one thing, but it doesn't become a real-world solution until you can make it reliably, make it cheaply, and make it at an absolutely massive scale. This is where the really tough engineering challenges kick in. So let's quickly look at the pros and cons for each. The core shell designs? Super stable. But creating those perfect tiny coats of armor can be a complex, multi-step process, which could mean expensive. Porous and hollow structures, fantastic at managing the swelling, but all that empty space means you might pack less energy into the same size battery. And the nanowires? Awesome electrical performance, but the ways we grow them right now can be kind of slow and costly to scale up for mass production. So what it all boils down to is this. The winner in this race won't necessarily be the design that performs best in a pristine lab. It'll be the one that hits that perfect sweet spot, that magical balance of amazing performance, low cost, and a manufacturing process simple enough to be done over and over again, billions of times. Honestly, this whole quest to tame silicon is one of the most exciting stories in science right now. We have this incredible promise of a tenfold battery improvement, and we have these brilliant nano-engineering strategies to get us there. So the final question really isn't if we'll solve this problem, but how? And which of these incredible designs will be the one to finally unlock silicon's true potential and power all of our futures?